Oh, hi there. Thanks for showing up for your learning. And now we're going to take a look at stretches and reflections. This, if you think that the H value kind of flipping signs and that is like a mildly weird, I got weirdness for you today, but I hope to make it super clear. Let's go through some examples. So let's take a look at these two functions where we start with a function f of x. This is our parent function here. And I'm going to make my pen really thin because I'm going to write lots of notes today. And here's my parent function. That's just my y equals x squared. All right. And then we're going to say, well, what are we doing to it here? If we have a g of x that's minus 2x squared, we can describe that as a vertical reflection over the x-axis. So that would create a new function that would look like this. Same shape, but just like Narcissus looking into the pond and seeing his own reflection there. And then the water is a little bit deceptive because it makes us look skinnier than we are. Because it's also a vertical stretch by factor of 2. It's like a carnival mirror. Have you ever thought of stretches and reflections, like looking at your function in a carnival mirror?
No.
Well, you came to the right place, Mrs. Hall. Something I can help you with?
Yes, I was wondering. You guys write in the window sometimes, right?
Sometimes.
Do you need special markers, or can you just use
whiteboard markers work, but like use black or purple, something really dark.
All right, cool. Thank you. Have fun, everybody.
Bye. So we're also stretching it by factor 2. So that would be, instead of like this, Narcissus looks even skinnier than he usually is. No wonder he falls in love with his own reflection. Us men are so vain. Okay, so anyway. All right. So that's what would happen if we're doing g of x. Now this is working, I want just to point out, like purely visually. And with these things, you want to have that kind of visual mental whiteboard working where you see x squared, you see it reflect, and you see it stretch. If you're having trouble seeing those things, I recommend you play in Desmos. So I have in here Desmos. Oh, I'm going to reload this one because we were playing with this a fair bit earlier. Just going to go in and reload my double transforms. Open the graph. There we go. Open double transforms. Here we go. So if I have f of x is equal to x squared, and I look at my transform g of x, oops, let's open that up. And I'm going to set all these, for some reason I saved it not at identity values. They should be at identity values. D and C, if you will recall, are adding or subtracting to inputs and outputs. That's a topic for tomorrow, D and C. Okay, but A and K are what we're looking at today. A is when I multiply outputs, and K is when I multiply inputs. So here we were looking at this transformation, negative 2x squared. So if you want help visualizing that, you grab your A slider and you take it from 1, which is the multiplicative identity, and you yank that down to minus 2. And then you'll see roughly what I described. Here's a Narcissus. He's looking in the pond. He sees himself. He kisses his own reflection because he's like that. And he's gotten skinnier. See that in your mind? That's working visually. Today we're going to be working with graphs, with tables going point by point, and with equations to find the new equation of the thing we're looking at. You always want to be strong in these 3 skills, or at least strong in 2 of them, so that you have 2 different ways of doing a problem. Well, let's keep going, everyone. Now, if we look at h of x is equal to 4x squared, this up here is an A transformation. Okay? This over here is a K transformation. We are multiplying the input directly. So we could use transformation language and say h of x is equal to f of 4x. This is a statement saying I want to take this function f of x, and instead of substituting x in for x, I'm going to substitute in 4x for x. It would create this expression. Yeah. So you substitute in what you see in those little brackets. That's always true. Okay? So let's explore what happens when we do h of x is equal to 4x squared. It says over here it's a horizontal compression by factor 1/4. Oh my goodness, it's like spoiler alert. That's the spoiler of what I'm going to show you in Desmos right now. And it should feel a little weird. Remember how I'm trying to get you convinced that the minus h is mildly weird? This is, I think, super weird. Let's take a look at it in Desmos. So I'm going to reset this a value back to 1 so that I get the same function again. And I'm going to actually just change my zoom level so I can show you things a little bit clearer. And I'm going to show you some stuff at the y value is equal to 4 and the y value is equal to 6. Let's take a look at these two places. No, let's not do 6. That's craziness. Let's do 16. There. And change the zoom value just slightly so we can see all those places. Here's our original function, and it has points at 2, 4 and points at 4, 16. Those are our squares. This is not surprising. Now, let's go inside the guts of g of x and just change this k to 4. So it looks like a vertical stretch. Do you agree?
Yeah.
Like it's been stretched vertically. But if you check, you'll find it's not been stretched vertically by factor 4. You want to see algebraically why that's true?
Yeah.
I'll show you. So over here, we know that this is f of 4x, right? So if I do f of 4x is equal to h of x, that's the same thing as taking f of x, but instead of x, substituting 4x in for x. Notice that that's this function here. Okay, so let's algebraically work that out. This is equal to, write it out as a multiplication if you really want to be very clear, 4x times 4x. Notice that in this case, the 4 goes along for the square ride, and we end up with 16x squared. So it's equivalent in this case to a vertical stretch by factor 16. And that's not how I want you to understand K transformations. Watch how I want you to understand K transformations. Okay, so here, this point here, it used to be at 2, 4. That was 2 squared is 4. Now that point got pulled towards the y-axis. It's not at 2, 4 anymore. It's at 1/2 4. So what we did to move this point over was we divided our x value by the K transformation. We divided 2 by 4 to get 1/2. Let's take a look at this point, 4, 16. Where do you predict this point to be?
4.
So if we take a look at this point up here, 416, we divide the x value by 4, we get 116. Because we are multiplying it by 4 here. This is the same thing. I'll write out the without this weird transformation stuff. This is we'll call it j of x because I'm Mr. Jennings is equal to bracket 4x and bracket squared. There it is. See, same thing. I showed you algebraically already. It was 4x all squared. That's different than 4 as a vertical stretch factor. It's more 4 as a horizontal squeeze. When multiplying inputs, divide your x values by what you're multiplying by. That's what you can do here. Okay? So, pretty weird, right? Yeah, I think that's kind of weird. This is weird when you first see it, but you'll get used to it. Don't worry. Okay, so that's what we mean by a horizontal compression by factor 1/4. Multiply all those x values by 1/4, you'll find the new function. In the case of a quadratic function, that can be the same as some other vertical stretch, but it's harder to imagine it as 16, stretching it up. But if you take a look at step pattern, it shouldn't surprise us that we have the point 116 here because it's algebraically equivalent to y is equal to 16x squared. So I take my step pattern, multiply it by 16. Instead of stepping up by 1, I stepped up by 16. Okay. Now, if I set this back to identity, and I show you some A transformations, I'm going to take you back to the comfortable world of A transformations. Let's take a look at these lines. X is equal to 1, and x is equal to -2. Okay, and we'll take a look at some of the values in here, and we'll increase our zoom so we can see them happening. And like this. Okay, so here are some points that are on my initial parabola. The points 1, 1, and -2, 4. Okay? Those are on y equals x squared. I'm now going to transform this function with an A transformation. Let's go to 2. So if I transform A to 2, what we'll notice is this new transform function, instead of this point being at 1, 1, it got stretched up to 2, 1, 2. This one, instead of being at negative 2, 4, it's now been stretched up to negative 2, 8. So all the y values, the x values didn't change. All the y values were multiplied by 2. So that's when I have a is 2, when I'm multiplying the function by 2. That's there. That's what would happen in those cases. That's this function here. Oh, negative 2x. Let's take a look at negative 2x. If I make a negative 2, here we go. And we increase our zoom there. So there is the initial one, 1, 1, got reflected and then stretched down to 1, negative 2. This is with an a value of negative 2. This is negative 2x squared. So we're just multiplying our y values by negative 2. Super intuitive. This one is negative 2, 4, goes to negative 2, negative 8. Pretty straightforward. It's all just multiplied by that new stretch factor. Okay. Let's keep going. So now, the steps that we want to take to transform parent functions when we're working with a table, this is what we're going to do, is first determine the parent function. So in this case, we found that our parent function was x squared. And then you can create a table of values for your parent function. And then determine what's called the transformation values, or I call this the transformation point. And apply the transformation point to obtain the new points in the new function. And then plot the new points. This is how you do this with a table of values. So let's take a look at an example of how we could go through this. Do people want a picture of that, or can I keep going? Yeah, grab a picture if you need a picture. And I'll put this in the D2L. This one I'll put in the D2L.
Are we going to do an example of this?
Yeah.
Oh,
Yeah, right next.
Determine transformation value.
I wish that was in the video. I think we just started it. Okay, let's go. Let's do an example. So let's graph the function g of x is equal to negative 2 times 2x squared. So here I notice that I have an A transformation and a K transformation. A is equal to negative 2. K is equal to 2. Okay? Now, what's the role of these transformations when transforming these functions? Well, when I have a point x, y in my parent function, and I want to find the point in the transformed function, what I do is I take my a value here and I multiply all of my outputs by negative 2. That's what we were seeing here in this Desmos graph. All of the y inputs got multiplied by negative 2.
Not the x.
Not the x's, just the y's. That was for the a transformation. But in this case, we're also applying a k transformation here. And the role of this k transformation is to divide my inputs, divide my x values. So my transformation point will look like this. X over 2 is what happens to my x values, and negative 2y is what happens to my y values. I have a beautiful graph of this parabola here, and I encourage you to extend your graph to the point 3, 9 and negative 3, 9, so you have a beautiful parabola that's kind of finished there. Beautiful, right? Just like a thing of beauty when I draw a parabola. Oh my goodness. And sorry? Oh, because the k value is 2. And k's role is, watch out, seasickness, horizontal compression. Okay? We get horizontal compression by a factor of, put your k value on the bottom of the fraction. A values multiply y, k values divide y. Now I'm going to point back at that board over there where we're looking at vertex form parabolas, and we saw k values over there. So, oh geez, I forgot about that whole k value thing. When we add to the output, then it lifts everything up. It's adding on. when you have the h value, it has to flip signs. Instead of adding, it subtracts. The k values here, instead of multiplying, they divide. They're similar to sign flippers. They're multiplication division flippers. They go on the bottom.
So k values divide x, y values multiply.
Multiply y, yes. Yeah.
Right, so a values multiply y and x values divide x.
K values divide x.
K values.
So I'm going to copy out this transformation point down here. I know that I'm going to have x divided by 2 because k is 2, and negative 2 times y because a is negative 2. Okay? And I'm going to show you how to work point by point to transform this parabola and regraph it. All right? Let's zoom in on our table of values. We have a handy dandy already prepared for us table of values for this quadratic. Let's move me out of the way and get that such so that we can see that transformation point. So for the new transform function, x, and this is g of x, I believe. This one, instead of saying y, you could also say f of x. It's our parent function, right? G of x is that, and our parent function is f of x is x squared. Okay. So let's apply this transformation point to all of these things. First, this 4 is a y value. It gets multiplied by negative 2, so that's going to map to negative 8. This negative 2 gets divided by 2, so that will give us negative 1. Now let's put the point negative 1, negative 8 on our parabola. And we're going to do that, and I promised you a different color here. I'm going to continue in orange. Okay, so it's negative 1, negative 8. It's right there. All right. Negative 1, 1. Well, 1, we multiply that by negative 2y, so that became negative 2. We'll just take 1 times negative 2. It gives us negative 2. And then negative 1 divide by 2 gives us negative 1/2. Okay, so that's a new point. Negative 1/2, negative 2. Zoom in, move over, graph it as accurately as possible. Here's negative 1, so negative 1/2, and at minus 2, boop, right there. Okay, nice big point. All right, let's move over, change the zoom. 0, 0. I divide 0 by 2, and I get 0. I multiply 0 by negative 2, and I get 0. Ah, the vertex didn't change in this transformation. Cool. They stay the same. I wonder why. Because those values were 0. They're both 0, so they don't change when we stretch it. So now let's check 1, 1. We divide 1 by 2 and get 1/2. We multiply 1 by negative 2 and get negative 2. And then let's plot that one. Ooh, seasickness. Sorry about that. There it is at 1/2 negative 2. Boop. And then the last one by symmetry is just going to be down there. So I can also work graphically and point by point as I'm going. Oops, zoomed the wrong way. There we go. 2, 4. Do we divide 2 by 2 and we get 1? We multiply 4 by negative 2 to get negative 8. That's that point there, 1, negative 8. Then we draw our new parabola. It really looks like a stretch factor of negative 8, doesn't it? Because it goes through the point 1, 8. Its step pattern is 1 over 8 down. So we would expect like some A transformation of negative 8 if we work this out algebraically. Let's work this out algebraically, people. You want to be able to work it out point by point, like I just showed you, graphically, just by stretching it and squeezing it, and then also algebraically by finding the new equation. So I know g of x is a transformed f of x, and it's equal to negative 2 multiplied by 2x all squared. And that's equal to negative 2 times 4x squared. Oh, sorry, not what I just wrote. No. No! 4x squared. See, I squared the 2x and got 4x squared. And then that's equal to negative 8x squared. So no surprise there. The algebra matches working point by point, matches what we get if we just stretch the thing and squeeze the thing.
Oh, I see.
Okay. Now I want to highlight that the vertex didn't move when we applied those transformations. The reason it doesn't move point by point is because 0 would map to 0 when I divide it or multiply it by anything. And then, so that's what we call an invariant point under these transformations. Graphically, when I reflect and stretch, it doesn't move. And algebraically, we'll see here that this is in vertex form, and its vertex form is 0, 0, negative 8x squared. So it doesn't move algebraically either. Okay, let's keep going. Next example. Sure.
Are we gonna answer?
There's still questions.
Yeah.
Oh, there's still questions? Oh, okay, yeah. All right, I forgot I put extra questions on your sheet.
Yeah.
Do you know how to answer these questions? I forgot what the questions are.
How did
Yeah.
transform?
How did A and K transform this function?
Very similar.
What did A do?
It multiplied the y value and stretched the y value.
Yeah, A is just a stretch. It's a vertical stretch by factor A. What did K do?
It brought in the x value, like it crunched it.
K values squeeze the X values. They compress by their factor. So we want to think of K as a compressor. It's like in Star Wars, the garbage compactor. That's like the Death Star turning up the K value of the inside of the garbage compactor. Crash. It's like, yeah.
What did they do? Yeah.
A is stretched vertically.
It stretched it like this, and then the other was just like
Squeeze
rubbed
it.
in like this.
All right, carry on a bit.
1 second.
Got one more example to do before I release you to some textbook problems. I can't believe how much faster we are than the morning. This is going much better.
What is the new?
How's our confusion level? Here,
100%.
here,
What is the new?
100% confused or 100% good?
It makes sense. Like not makes sense.
But you think you can do it, right?
What is the new function though?
Oh, what's the new function?
Yeah.
Negative 8x squared.
That's it.
Yeah. Or you could write it as this, but that would not be simplified, right? So you could write it that way. That's our new function, negative 8x squared. So you want to have all three skills. Can you work by a table by creating a transformation point, something that looks like this, and then applying this transformation to each point, point by point? That transforms into this. Can you work visually, imagining it flip, stretch, and squeeze?
It's always going to be flipped.
No, because there's a negative there, right?
Right. Okay, but when it's negative, it's okay.
Yeah. The negative A value flips it in the x-axis. What do you think a negative K value would do?
Or bring it up. I don't know. No. What?
Squeeze it in.
It squeezes it out. Yeah.
Well, let's take a look in Desmos. I'll show you in Desmos. So here we go. If I take the K value and make it negative here, oh, it doesn't do anything.
Oh yeah.
Do you believe me that it doesn't do anything?
Isn't it like a right to the square? Like that.
Yeah, something weird's going on there.
But isn't it doing something? It's like spinning it around.
Yeah.
Like this.
I'm kind of cheating here, everyone. So let me prepare another example for you. And I'm just going to restore these to identity, K and A. And I'm going to recreate our new function, the one that you're going to look at on the next page. It has a D value of, I think it was 3. Wait, what was 2? 2. The next one is, yeah, D value of 2 and a C value of -1. C value -1. Okay. So now let's not look at f of x. We're not going to look at these two lines, so I'm just going to kick them out. Okay, here's the function that we're going to consider next. And I just want to show you what happens when we start applying transformations to this function. Let's restore a to 0. Okay. Now, watch what a does when I take this function and transform it around. I'm just going to let a play. Okay, so there, as a gets bigger, we get bigger vertical stretch. As a gets negative, we get other vertical stretch. But notice that the vertex is moving now. Notice that all the points are moving except for 2. We have 2 invariant points. What are they?
X-intercepts.
The x-intercepts are not moving. Why not? Why are the x-intercepts not moving when a is changing? It's a family of functions with the same roots. But if we're thinking point by point, a is multiplying the y values. It's multiplying the y values of this function.
Yeah.
But these have y value 0. So it doesn't much matter what we multiply them by, right?
Yeah.
Let's change this to orange. I like orange.
Oh, sorry, not affected.
So there you can see h of x is, we're just changing this a value, and it's changing the function g of x. There's the g of x function right there. Okay, so you can see that transformation happening. Now let's set that back to identity. Oh, I missed. Let's bring it back. Okay, notice that they're the same. Now let's let k play. Actually, I'm just going to move k. This is k getting big. See, as k gets big, everything gets squeezed towards the y-axis. Do you see the point that's not moving here?
Y value.
The y-intercept, yes. As k gets smaller than 1, notice we get horizontal enlargement. It gets stretched horizontally as k is between 0 and 1. Because we're dividing by a fraction, or we're dividing by something smaller than 1. So that's like multiplying by a bigger number. Okay. As k becomes 0, it becomes a line briefly. And then, here's k is -1. What do you see has happened?
Flipped over. They reflected over the y-axis.
That's why we couldn't see the negative k transformation before, because the parabola was symmetrical around the y-axis. Now the parabola is no longer symmetrical around the y-axis, and you can see the negative k value here. When I multiply the inputs, it flips this point, makes it negative. It flipped this input, made it negative, because I'm now dividing all those x values by -1.
Not like how is this
How do we use these ideas? These ideas seem weird in the beginning. It's just so magnificently useful. Okay? Don't let me geek out over that, because I do want to give you some time to do some practice problems today. But we'll chat. Now, as k becomes something like -2, that's going to be one of the functions I want you to consider here. So let's visually see it. When k is -2, let's just take a look at the vertex here. That was the point 2, -1. But then we divide 2 by -2. We divide 2 by this -2 value, and we get the point -1, -1. The y value didn't change. It's just the x value got divided by the k transformation. See it? Okay, I hope so. Let's practice some. Let's practice some together. So here we want to graph two different functions, and sorry, I forgot. I should have given you 2 tables of values that you can complete. First, get your table of values for the parent function. Someone fill in this table of values for me. So what points do we have here on our parent function? So we have 1, 0, 2, -1. Okay. Oh, I also see 3, 0. Sorry, 0, 3, and 3, 0 are a few of the points, right? Here's 3, 0. Here's 0, 3. And we could even go over 1 and up 5 to go up to that point there. And over 1 and up 5 to that point there if we wanted. Okay, but I don't think we're going to look at those points. They're going to be a little awkward. Okay. And now, let's create the transform function for, let's do this one. H of x is f of -2x. Okay. So our transformation point is going to take values x, y, and map them where? I see this as a k transformation because it's multiplying the inputs directly. K transformations divide my x values. So my transformation point will look like x over -2. Y. Y will be unchanged. So let's do it to these 4 points. 1, 0 will become 1 over 2, but it's -0. So let's put that on. That's the point 0 in the y and -1/2 over here. Oh, I want to do this another color. So we see it in another color, orange. There we go. Boop. I can zoom so you can see that that's at the point 1/2, -1/2, 0. Okay, there we go. And let's keep going. 2, -1. Oh, my transformation point is divide the x values by -2. So 2 divided by -2 is -1. And that will still be at -1. That was the vertex that we saw just before. Boop, right there. And then 0, 3. Well, 0, if I divide that by -2, is still 0. And 3 is still 3. So that point is the same. Point by point, we see that the y-intercept didn't change. And then, what's this other point here? 3, 0. Well, 3 divided by -2 is -3 over 2. And 0 is just still 0, because we're not changing those. That's -3 over 2, or -1.5. Okay? So here's our new parabola. It's going to come down here, touch the other parabola, intersect that parabola at that point, go through those points, and then fly up here, go through that point, and off to infinity and beyond. All right? Now, If you are working from the parabola and working more visually in your mind, you can even do visually plus point by point. And this is how I think about it as I'm doing that. I think, okay, all of my points are going to have the same y value, so that's not going to change. So if I say grab this point here, and I'm going to apply a transformation of -2 equals k, I know I'm going to take x values and divide them by the k value. So I first reflect it in the y-axis, so it goes over here, and then I divide the x value by 2, so it pops back there. This one, I reflect it over here, and it's at 1, and I divide it by 2, and it's at 1/2. This one, I reflect it over here and divide it by 2, so it goes there. And so I can kind of visually map the points over and move them along. Have a question for me? Just letting it all sink in and the glory of these ideas. So rather than working table of values, maybe we can do g of x without that. So g of x is -2f of x. I see this is, and I'm just going to erase that junk that I just drew because I know it's hard to look at. Okay, and we're going to start a new color here. We'll go with a red. And we're going to say g of x is equal to -2f of x. So in this case, it's a transformation because I'm multiplying the output of the function. That's f. F of x is the x squared. Multiply the output. So that's a is -2. So that creates a transformation point of x values will remain unchanged. And y values will all be multiplied by -2. -2y. So working visually, these points here are going to fly off the graph because they're going to flip down and then be multiplied by -2. So they're going to fly off the bottom of the graph. We don't need those. This point here, oh, it's a good point. It reflects in the x-axis now, down there to -3, and then gets doubled. So it goes to -6. Okay, so there's one of my points. This point here gets reflected in the x-axis and then doubled. So it stays exactly where it is. This point, same story. This point here, by symmetry, will go down here to -3 and then get doubled. So it's down there. This point here gets reflected in the y-axis there and then doubled. So my new parabola goes here. Mirom. Sound effects always optional, but highly encouraged.
We're using the parent function, right? In comparison.
Yeah, I'm using that. I hesitate to call that a parent function because really the parent function is x squared.
The one right here.
Yeah, it's already a transformed x squared. Yeah.
And then that's the new one. Wait, so we're using x squared?
No, we're using this function here, f of x, which is equal to, given f of x on the graph at the right,
Yeah.
f of x is equal to, well, let's take a look at f of x. I'm just going to erase all my graphs. There's f of x. Okay. And what was its equation all along? We started with a table of values, but we can also work equations here. What's its equation? Give it to me in vertex form. Oh, Mr. Jennings, I see the step pattern is 1, so the stretch factor is 1. So it's just x something squared plus something.
Oh, -2.
X minus 2
Yeah, and then
minus 1. Yes, good, thank you. So this was the original function here, and we created another one that looked like this, boop, 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 and down all the way to this point. Okay, that was g of x. Well, we multiplied it by -2. Okay, let me show you how we would do that algebraically, and then my lesson is done. Okay, so algebraically now, we've looked at it visually, we've looked at it transforming point by point, and now we're going to look algebraically. And I'm going to copy these things out carefully down here. F of x is equal to x minus 2 squared minus 1. That's a vertex form parabola that we just saw with its vertex over +2 minus 1 that opens this way. We saw that it has a y-intercept of +3. Okay, so those are some of its points and roots at 1, 0, and 3, 0. Cool. All right, now we want to know g of x which is equal to, I'm going to multiply f of x by minus 2. Okay. That was our transformation. This is where we put a value transformations. They multiply the outputs of functions. So g of x, let's substitute f of x in there for f of x, is equal to minus 2, big bracket, x minus 2 squared minus 1, big bracket. That's f of x multiplied by minus 2.
You're substituting f of x.
I'm substituting a whole function in there where it says to substitute a whole function. Okay.
Wait, why is it f of x there? Is that just the same thing?
Because that was the definition we were given for g of x.
Right, but it could have been like x squared.
Here's g of x is equal to minus 2 f of x.
But it's also f negative 2x. It's also h of x.
There's also h of x. I'm not looking at h of x right now. I'm just looking at g of x. If you want, I can look at h of x next, algebraically. So now what I can do is expand this into standard form and see what we find. Okay, this is equal to negative 2 multiplied by big brackets, x minus 2 times x minus 2 minus 1, big brackets. Note that Desmos doesn't like square brackets. Don't use square brackets in Desmos. But in your math work, it's nice to have your outermost brackets be square. It's very clear. Okay, then I just evaluate. This is equal to minus 2 multiplied by, now smaller brackets, fine, x squared minus 4x plus 4 minus 1, so plus 3. Okay, note that's just f of x in there. And that shouldn't surprise us because we knew that it had a y-intercept of 3. It was descending when it crossed the y-axis at a slope of minus 4. So it's the same thing.
Oh, so that's like standard form.
This is standard form f of x. I've just converted it from vertex form because you gave me f of x's equation in vertex form, so you gave me extra work to do. Thanks very much. And now I'm going to multiply everything by minus 2. So this is equal to negative 2x squared plus 8x minus 6. That's g of x.
Oh, so that's the one.
That's the transformed equation. Let's take a look at this equation and what we'd expect to see. I would expect to see a y-intercept of minus 6. I would expect to see a parabola opening downwards with stretch factor 2. And I would expect to see behavior around the y-axis of rising sharply. Let's see what we had. Oh, look at this. Opening downwards, y-intercept of 6, behavior at x-axis of rising sharply. Wow. Algebraically, point by point, and working graphically all give you the same thing. You now may be really fuzzy on 3 different ways to climb a mountain. As you get good at one of those ways, I believe it will strengthen your other 2 ways of climbing the mountain. If you can be like me and strong at algebra, strong at changing point by point, and strong at visualizing, then you'll be done your test in 20 minutes, this unit.
Did you just infer?
Next week.
Did you just infer to get 4 negative 6 or no?
Where?
Or it's
4 negative 6?
Yeah. Did you just infer that?
4
Or
negative
how did you
6.
get- how did you
Oh,
get
this
that
one
from-
here?
Yeah, how did you get that from your table of values?
Oh, I didn't do a table of values. I did it visually. But I kind of did a table of values. I took this here.
Yeah.
I reflected it in the y-axis, so it went there. That was the negative part of the a.
So that's
And then I stretched it by factor 2 to get down there. So I took the point 4, 3,
yeah.
and multiplied 3 by negative 2
Yeah.
to get 4, negative 6.
Okay, so okay.
Kind of 2 different ways of saying the same thing. One is working visually, and one is working table of values.
So just basically what we need is like k divides x and a multiplies y. Yeah.
K divides x and a multiplies y. Yes, you're right. Yes, you're right. Yes. When you're working point by point,
Wait, so
Is there a different way to work with it?
algebraically
Oh.
or visually.
So
A stretches vertically, which is the same thing as multiplying your y values,
Yes.
and K compresses horizontally, which is the same thing as dividing your x values. And then working algebraically is just get your algebra muscles out and find the equation in the new function.
Which is easier.
Okay, sure. If you think that's easier, do that.
so then
But when you get to sinusoidal functions, you'll want to know these ideas. Okay, everyone. So that's me. Any questions, hit me up by email if you're Team Learn at Home. If you're not Team Learn at Home, ask me questions now. Bye.
so the